In this lesson, we're going to take a look at an old idea in a kind of new way. So we looked at compound angles, where we have some combination of two angles that don't necessarily make a special triangle individually, but if you put them together, they could, or you can break them apart into special triangles. But the idea of a double angle is what happens if x and y actually happen to be the same angle. They're both equal. Well, we can take this idea and create a double angle. So instead of saying sine of x plus y, what about if it was x plus x, as in x is equal to y? They happen to be the same angle. Well, every time I see an x, sorry, a y, like this one, I can replace it with an x now. And if you will, this now becomes two of the same things, or in other words, 2 sine x cos x. On the left side, we have x plus x, or in other words, 2x. We call this a double angle. Call it double angle because it's made up of two of the same angles. And we can show this actually works. Okay. Let's take a look at this expression here, that the sine of 60, which is a special triangle, is really made up of just the sine of two 30s. Okay, so from special triangles, 60, and let's do the 30 also. Okay, the sine of 60, so sir, 6 or ticks, make sure we're using the 60-degree one, would be y over r. So how about root 3 over 2? That's the sine of 60. On this side, the sine of two 30s, well, if we take our formula up here, a double angle is made up of 2, that's this guy, times the sine of whatever x happens to be. In this case, x is 30, right? And the cos of 30. We'll get 2 times, we're going to use the other triangle now, the 30 triangle. Sine of that would be root 3 over 2 times the cos of 30. Oops. Hang on. The 1 over 2. Got ahead of myself there. Cos of 30 is the root 3 over 2 one. It's all stuck together, so it's all multiplying, right? When you stick together like that. Okay, up top, if we multiply it all together, 2 times 1 times root 3 is 2 root 3. 2 times 2 is 4. We can reduce this fraction, just call it root 3 over 2. And what do you know? Those are the same. You know, obviously, if we had a 60, we would just use our special triangles because it's faster. But we can use the double angle formula to get the same answer when we don't necessarily have a special triangle. And this idea can also be extended to cos double angles. So if you made x plus x become the same angle, so a double angle, you replace all the y's with x's. So cos cos minus sine sine, or in other words, cos squared minus sine squared. And if you use the identity, sine squared plus cos squared is 1, you can actually do some replacings. So for instance, if I saw cos squared, I can make that 1 minus sine squared. And that'll give you a different version of the cos double angle. And you can do a third one, and you can replace the sine, and you get a third version. So these are just rearrangements of this guy, and you can use any one of those interchangeably. You could also do tan. This would be the tan formula. Now, obviously, I don't expect you to memorize these. They're on your identity sheet. We're just going to start using them when we have double angles. So let's get warmed up for that. Could you rewrite these expressions as double angles? The sine of 100 is a single angle, but I could rewrite that as the sine of two 50s. And if I saw that being a double angle, this is my x, based on our formula from back here, this double angle, I could write that as 2 times the sine of 50 times the cos of 50. That's just 2 sine x cos x, where x is 50. And we're not calculating these ones, we're just rewriting them. How about the cos of 4 thetas? Well, we can write that as the cos of 2 thetas. That makes 4 thetas. And you have some choices here. You could do any one of these three. So you choose. It doesn't really make a difference which one. Let's pick one of those. We're just practicing writing these things. So maybe cos squared of 2 theta minus sine squared of 2 theta. That's the first one. Or if you want to do one of the other ones, I don't know, try one just for random sake. This is also like saying 1 minus 2 sine squared of 2 thetas. We could even rewrite tan x as a double angle. This is worth the same as the tan of 2 x over 2's. It's like an angle cut in half, right? If you multiply this together, you get back to that. Well, the double angle for tan is, it's off right here, 2 times tan x. So 2 times tan of our x is this angle, so x over 2, over 1 minus tan squared, x over 2. Sometimes you'll see the brackets there, and sometimes you won't. They should have brackets there, we just don't always write them in. Those are different ways of writing expressions as double angles. Okay, let's try some other stuff. Can we express as a single ratio and then evaluate? So we're actually going to calculate these ones. Hey, I look at this one and I say to myself, hey, this is cos squared minus a sine squared. And now we're into radians. That's okay. Well, cos squared minus sine squared is this guy, cos of a double angle. This is like saying cos of 2, if these are our x's, 2 of those, so 2 pi over 8. Well, I can multiply pi over 8 times 2, I'll get 2 pi over 8, or in other words, pi over 4. And pi over 4 is a special triangle. Okay, pi over 4 is the isosceles one, and we're doing cos, so x over r, and we'll rationalize that. So how about root 2 over 2? And while we couldn't do these ones, because pi over 8 is not special, when I put them back together, it becomes a special one. Okay, I'll go to the next one, 2 tan. Okay, that's the tan of 2 of whatever x happens to be, 5 pi over 12, which you could write as the tan of 10 pi over 12. And just multiply fractions, go straight across. If we can reduce that fraction, we'll get 5 pi over 6. So that's a special one. That's 5 pi over 6, because this would be 6 pi over 6. Takes that pi over 6, and pi over 3. Root 3 is across from the 3. It's negative 2 and 1. We want tan, so tix says y over x. We'll fix that one, we'll rationalize and move the negative to the top. And there's your expression. Again, 5 pi over 12 wasn't possible, but when I fix it, turn it into a special triangle, it is. Okay, let's do some other things with these double angles. Okay, we're given that the sine of an angle is 4/5, so not special this time. And x lies between pi over 2 and pi. What that's telling me is where to draw it. Pi over 2 is here, and pi is over here, so my angle x has to be between those. So there's my triangle. Okay, x is this guy, but we know we actually use the acute angle in the triangle. Okay, sine is sur, so that's my y value and my r value, which means I'm missing the x value. But I can find it, use the idea of Pythagoras, or a squared plus b squared equals c squared, or in this case, x squared plus y squared equals r squared. And then we'll rearrange this. 25 minus 16 is 9, so x must be 3. But because it's going to the left, let's make it negative. And we're going to use this triangle without ever actually knowing the angle to figure out what these ratios are worth. Our first ratio asks us for the sine of 2x. I don't have double angles. However, I can convert this into regular angles. If I know what angle x is, or at least its ratio for it, they told me that sine x is this right here, I can replace sine x with 4/5. I can do the same with cos x, except they didn't tell me what it was in the question. But in my diagram here, here's my x value and my r value. So I can say x over r, and that's what its ratio is worth. I don't actually need to know the angles to know what the ratio is worth. Okay, fractions will go straight across, so 2 times 4 times negative 3 is negative 24, and on the bottom, 25. That's the value of sine 2x. Let's try tan 2x. Tan 2x also has a double angle formula. It's 2 tan x over 1 minus tan squared. Okay, they didn't tell us tan in the question, but ticks y and x tells me I'm going to have 2 times 4 over negative 3 over 1 minus 4 over negative 3 squared. Now, we don't really like fractions over fractions. We're going to split this up. So on the top, I'm going to do my multiplying. I'll get 8 over negative 3. I'm going to turn this dividing line into a dividing sign. On the bottom, I'll have 1 minus. I'm going to do my exponent. 4 squared is 16. Negative 3 squared is 9. Okay? We try to avoid this fraction over fraction business. Okay, I got negative 8/3. Just move the fraction negative sign to the top. Divided by, we need a common denominator there. So 1 over 1. So how about 9 over 9? And 9 minus 16 is negative 7 ninths. If you're not sure about that, use your fraction button. Or think to yourself, this is 9 ninths minus 16 ninths. Okay, to divide fractions, we've got to flip and multiply. So I'm going to take the second one, it's reciprocal, and flip it upside down. You can put this negative sign wherever you want to. I like them on the top. 8 times 9 is 72 over 21. Nice answer, except for I think we can reduce that one. And that one should reduce to 12/7. Okay, and I think that's it. That's a 12/7. How about 24/7? My bad, guys. Divided by 3. Okay, next. Okay. I get you guys to try one of these. Same idea, different setup slightly. Okay, give an angle x, set is between pi over 2 and pi. And this time they're telling us the sine squared is that. Can we find the exact values? So start by drawing a picture. It tells us where to draw it. It tells me it's between pi over 2 and pi, which means it's there. It tells me that sine squared is 8 ninths. But we don't really want sine squared. We want to know what sine is. So how do we get rid of squaring something? How about we square root it? To square root a fraction, you can do the top and bottom parts separately. So how about root 8, because that doesn't come out nicely. And the square root of 9 is just 3. Now I've got my y value and my r value. So root 8 is my y. R is 3. I'm missing the x, but we can do Pythagoras like we did before. So x squared plus root 8 squared equals 3 squared. How about 3 squared minus root 8 squared? 3 squared is 9. Root 8 squared is just 8. So how about 9 minus 8? Or in other words, 1. Square root that and you get 1. Or in this case, negative 1. So going to the left. Okay, once you get your triangle, you actually have all the parts and pieces you need. Oops, move those numbers here. Okay, sine 2x is a double angle. 2 sine x cos x. Okay, our sine x we know is root 8 over 3. Our cos x is x over r. And we can multiply this together. We'll get negative 2 root 8 over 6. Oh, 3 times 3 doesn't make 6, Mr. Casella. How about 3 times 3 is 9? Okay. Sometimes you'll see this answer broken down because root 8 actually breaks down. Right? Root 8 is made up of root 4 times root 2. So you could also write this as negative 4 root 2 over 9. That's the same thing. Our book sometimes does it and sometimes doesn't, so just be aware. Okay, let's do cos. Cos, we have choices. We have three choices. I'm going to use cos squared minus sine squared. The reason I'm using that one is I already know what sine squared was. It told me in the question it was 8/9. Right? That's what this says right here. So cos squared is my x value, -1, over my r value, which is 3. I'm going to square that. So we got 1/9 minus 8/9. In this case, -7/9. That's not too bad. And then we got tan. Tan is not always our friend, but this time it actually is going to be because we have a cheat. Okay? Yes, we could use the formula. There is nothing wrong with using this formula. You have all the parts and pieces you need for it, but there's a faster formula we could use. We have an identity about tan. We know that tan is always worth sine over cos of whatever the angle is. In this case, the angle is 2x. So we'll put a 2x in those spots. And why would I use this? Well, I'm pretty sure sine 2x is right here. I'm pretty sure cos 2x is right here. So I can put those numbers right in. We'll get -4√2 over 9 divided by -7 over 9. As we said earlier, we don't really like fractions over fractions. So let's fix this. That really means that but to divide fractions, we have to flip and multiply. And if things show up on the top and the bottom and you're multiplying, we can actually cancel those. And we'll be left with negative times negative is a positive, so how about 4√2 over 7? And that's way faster than actually using the tan law, or the double angle for tan. Okay, let's try something a little bit different. For this one, we're going to step it up a little bit. Let's try and find the sine of 3x's. Can we do that? Of course we can. The question is how? If we think of this as the sine of 2x's plus 1x, pretty sure that's 3x's, now kind of make it look like a double angle, or a compound angle, if you will. Okay, this is two sines where the angles are now different from each other, right? Because 2x and 1x aren't the same things. It turns it back into a compound angle question. Well, we have a formula. If we have the sine of x plus y, it's on your identity sheets. It's really just the sine of the first angle, cos of the second, plus cos of the first angle, sine of the second. Or in our case, my first angle happens to be 2x's, and my second angle is 1x, plus the first angle, the second angle. And I'm pretty sure we know what sine 2x is. Back here, didn't we say sine 2x was this guy? So -4√2 over 9 times the cos of x. Well, cos of x, we said, well, on our diagram, cos of x is x over r, so -1/3, plus cos 2x, I think we did that one already, that's -7/9. And the sine of x, back here we said sine x was √8 over 3, or if you want to, 2√2 over 3. Look at that. Now we can do sine 3x. Just multiply these fractions together. We'll get 4√2 over 27 for the first one, minus 14√2 over 27. I'm pretty sure we can collect those and we'll end up with -10√2 over 27. Look at that. We now have a new version, a bigger one. We can combine double angles and compound angles. Okay. Really, we can actually combine these things and make new formulas. That last one was actually a triple angle formula. The sine of 3 theta, or 3x's, or whatever you want to, this answer we got here, could be done by just creating a new formula. Here's the formula for that. And we could prove that it's true if you wanted to. I could show you after. If you want to check it out, we could. but you can just trust me. We can also do the cos of a triple angle. We call these triple angles because 3 of an angle. Okay. Again, I wouldn't expect you to memorize that or even necessarily derive it, although we could. Not the end of the world. Just if it comes up, we can use it. Okay, last idea. We can actually prove things that involve double angles. Tricks for us. Get rid of double angles. They make things more complicated. Okay. So just like before, left side, right side, work on the complicated side. So on the left side of this one, I look to myself and I say, hey, there's some double angles in there. So let's get rid of those. I'm going to do the bottom first because this is an easy one to get rid of. The sine of 2x is 2 sine cos. It's the only one it is. But up top, we actually have 3 different versions of this. So you kind of have to think ahead to yourself and say, what do I need? I need cotangent. Just one single thing. Is there a way I can get rid of this plus 1? Well, there is. One of our identities for cos double angle has a minus 1 in it. If I use that one, 2 cos squared x minus 1 to replace this part, I have the plus 1 still. What's going to now happen with those 2 1s? They'll cancel each other out. So we'll end up with just that over that. And why is that helpful? Well, if you see the same thing on the top and the bottom and they're multiplying, you can cancel them. Like the 2's. 2 divided by 2 is just 1. Cancel it out. I got a cos on the bottom and 2 of them on the top. Well, if I cancel one of them out, I'm left with 1 cos on the top and 1 sine on the bottom, which I'm pretty sure is actually cotangent, which is what I wanted. Okay. So double angles, when you're talking about identities, well, they work. You usually want to try and get rid of them. Okay, you guys try the last one here. See if we can come up with. Pause it, try it. The left side's more complicated, obviously. No choices on the top one. Let's just get rid of that. Okay, on the right-hand side, though, we got some choices. So let's pick one. We may have to play with this a little bit, see what happens. What can I do here? I'm going to try the 2 cos one. Okay, on the left side, I think I can cancel these signs out because they're both the same and it's multiplying. That leaves me 2. Oh, I missed a squared here. 2 cos x. I cannot cancel things on the right-hand side, however, because there's a minus sign there, right? That minus 1. Okay, now how does that help us? Well, to subtract fractions, I need a common denominator. So I'm going to times this by cos x. Whenever I do the bottom, I'm going to do the top. That'll give me 2 cos squared x over cos minus, hey, 2 cos squared x minus 1 over cos. Oh, I see what's going to happen here. Maybe you guys do too. If we write this as a single fraction, I'll get 2 cos squareds minus 2 cos squareds. Be careful the next part, though. It's actually a plus 1, right? It's minus. These two cancel each other out, and I get 1 over cos x. That's just the same thing as saying secant x. And I'm pretty sure that's what we wanted. And look at that. We just proved our left side was our right side. Okay, now I got lucky, I guess, in that I picked the right cosine double angle formula to replace with, right? I picked this one. If I picked a different one, I may have to mess around a little bit, try some other things out. There's not a right way to do an identity. There's more efficient ways, but sometimes you got to play with them a little bit. Okay, that was a lot of stuff. We got to try a couple questions ourselves. Nothing super crazy in there. If you're stuck, come see me and send me questions. I'll help you out.